Okay, so for the final talk of this session, we have Pierluigi Niro, who is going to tell us about aspects of QED in 2+1 dimensions.
Yeah. So first of all, let me join the other speakers in thanking the organizer for the conference and inviting me here. So, okay, so today I'm going to talk about some aspects of quantum electrodynamics in 2+1 dimension. This is work that has been done end of last year together with Thomas Dumitrescu and Ryan Tongren, who are faculty at UCLA. And there was also some related work by Shai Chester and Zorko Margotsky around the same time that reached the same conclusion using different arguments. And if I manage, we'll also discuss some work in progress together with Thomas and Ken Intreligator, who is a faculty in San Diego, and Orsela, who is a postdoc at EPFL. Okay, so the general motivation to study quantum field theories in 3 dimensions is that, as you know very well, there is a correspondence between Euclidean quantum field theory and the statistical mechanics. So they can describe statistical system at thermodynamical equilibrium. And for instance, if you have a lattice system and then you do some coarse graining, then when the correlation length is much greater than the lattice spacing, the system is supposed to be described by a continuum field theory. And also, if you have a 4-dimensional QFT at high temperature, this is effectively described by a 3D QFT. So these are useful to study 3D QFTs. And then on a more theoretical point of view, the point is that 3D gauge theories are classically strongly coupled. This is because the gauge coupling has a classical mass dimension. And so these are a simplest example of strong coupling with respect to ordinary 4D gauge theories. And the theory I want to focus on is good old QED. So it's a U1 gauge theory. You have a Maxwell term, and there are NF massless Dirac fermions, which in 3 dimensions there are 2 components complex fermions. And I didn't write any Chen-Simons term, and it is well known that due to the parity anomaly, this is possible only if the number of fermions is even. I'm going to assume this throughout the talk, so NF is even, and the theory enjoys time reversal symmetry, because if NF is odd, this is not the case. Okay, so this is the theory we want to study. So what is the question we want to ask? Okay, what is the phase structure of the theory when you vary the number of fermions? So if NF is very large, you have a conformal field theory. You can prove exactly this. And then as long as you diminish the value of NF, there is a critical value NF star, below which the theory is not in the exit the conformal window. And so the question we want to focus is, okay, what is, so first question is, what is the value of NF star? So we cannot say anything about it, because only with it's a very strongly coupled problem, so only with numerical techniques you can estimate NF star. But the thing we want to ask is, okay, suppose that there is an NF star, what is the fate of the theory below this critical value? So before answering this question and telling you our proposal, I just want to focus on the 2 solvable corners of this diagram, which is NF equal to 0, which is just Maxwell theory, and large NF, which is solvable because it's a vector model. So Maxwell theory in 3 dimensions is dual to a theory of a compact scalar, right, which is referred to the dual photon. It's a periodic scalar, and the nice thing is that the magnetic symmetry that acts on monopole operators of the theory is actually just usually a usual traditional Noether current associated to the shift symmetry of the scalar. And so the monopole operators, which are disorder operators in the Maxwell presentation, in this presentation are just the vertex operator of sigma, and you see that they are acted by the shift symmetry with charge 1 or charge QM. And in this theory, which is basically an S1 sigma model, you see that the monopole condenses. So every time you think about a Coulomb phase in 3 dimensions, this is the same as saying there is a massless photon, and it's the same as saying that there is an S1 sigma model. So you have spontaneous symmetry breaking due to monopole condensation. Okay, this is a free theory, NF equal to 0. Then you can do large NF. Large NF, you can compute exactly the propagator of the photon, and you will see that in the AR you have a conformal-like behavior. So the theory is indeed a conformal field theory, and it's amenable to a systematic 1 over NF expansion, and you can compute whatever you want with at any order in 1 over NF. So now the question is, what is the fate of the theory for intermediate value of NF? Now, as I said, we have to resort to some other techniques, like numerical techniques and bootstrap analysis, which tells us that there are very strong indications that the theory flows to a CFT for any NF greater than 4. Remember, I'm focusing only on even NF, whereas NF equal to 2 is not a symmetry-preserving CFT. Okay. I'm going to show at the end that this is also compatible with some supersymmetric RG flows, which is the work in progress I mentioned. So in this talk, what I'm going to do is I'm going to assume that NF equal to 2 is the theory that is outside the conformal window, and I'm going to ask the question, okay, if it's not a CFT, what it is? But our story can be generalized to any even NF, but just for simplicity, I'm going to focus to the even case, to the NF equal to 2 case. Okay, so the first question you have to ask yourself is a kinematic question. So what are the symmetries and what are the anomalies of the theory? The symmetries is a U2 global symmetry that is made of an SU2, which is the rotating the fermions, the U1 magnetic symmetry, which persists even if you have matter fields. And if you're careful about discrete quotient, actually the true symmetry is not SU2 times U1, but is a U2. There is a common Z2 quotient. And then you have charge conjugation and time reversal. And the important things about this theory is that, first of all gauge invariant operators are bosons, so there are no fermions in this theory. Then, broadly speaking, all operators of the theory can be divided into non-monopole operators, so they don't carry any magnetic charge. And this means that they are a representation of SO3, right? You don't have these, so you just have SU2 divided by Z2, so SO3. An example is this triplet mass term, this bilinear, that is in the joint representation of SU2. And then you have monopole operators, which instead carry magnetic charge, and they are in a genuine representation of SU2. And the most important one, the hero of our story, is the monopole, which is in the fundamental of U2, which means that is a doublet of SU2 and has unit magnetic charge. In the back of your mind, you can think about the standard model of particle physics, and where this would be a gauge symmetry, of course, it's not a global symmetry. This would be the left, this would be the hypercharge, and the monopole is like the Higgs doublet, right? Which is both a doublet of SU2 and has some hypercharge. And the other important thing is that these symmetries have a Toft anomaly. So there is a mixed Toft anomaly between U2 and time reversal. And this can be written as a 4-dimensional anomaly inflow action, which is basically a theta term for the background gauge field with theta equal to pi. This is the second Chern class of U2, which is basically a combination of the instanton number for U1 and SU2. So already the presence of a mixed Toft anomaly tells you that in the infrared, the theory cannot be trivial, because otherwise you wouldn't match the anomaly. Okay, so let me go to our proposal, and then I will try to give some consistency check of why we think this is the case, of what happens. So our proposal is the following, that what you have is that the monopole is condensing, the minimal charge monopole is condensing, and you have spontaneous symmetry breaking of the U2 symmetry to U1, an unbroken U1 subgroup. And this is exactly the same what happens in the standard model, but here is a global symmetry. So you have 3 Nambu-Goldstone boson, and they parameterize the sigma model, which has a target space, which is S3. Now, this S3 is conveniently described with a Hopf map. So you given some monopole operator that has a VEV, you construct a projection from S3 to S2. And then to each point on the S3, you associate this vector n, which is a unit vector, which is in the triplet of SU2, but is uncharged under the magnetic symmetry. So the vice versa, if I give you n, you can reconstruct the full M up to a circle, right? Which is the S1 fiber over the S2 base. And the metric of the S3, it can be conveniently written in this way, in the Hopf coordinates. And so you see that there are 2 parameters that, okay, we don't know how to compute. It's a strongly coupled problem. But this is the metric of the sigma model. So the important thing is that our claim is that there are 3 Nambu-Goldstone bosons, 2 associated to the adjoint breaking, and 1 associated to this fiber, which is the dual photon, which can be interpreted as the dual photon. Okay, this is a representation of what I'm saying. So there is an S2, and each point on the S2, there is a fiber S1. So let's do an example. Let's take as a direction on the sphere, the north pole and the south pole, so the Z direction. And this preserves some U1 Cartan, no? The rotation around this axis. And you see that at the north pole, the monopole that is condensing has magnetic charge 1 and flavor charge 1. So under this plus combination is 1 charge, and then the minus combination is 0. But vice versa happens for the south pole. So this is really the statement that is a non-trivial fibration. So the target space is not S2 times S1, but is really S3. So what is the U1 that is preserved depends on the point where you are on the base. Now you can ask yourself, okay, what about the fermion bilinear, this time reversal fermion bilinear that I told you at the beginning? Our claim is that also this is condensing, but it condenses in a way that is already aligned with the Cartan direction preserved by the monopole. So you don't have any further symmetry breaking, and you have just alignment of the fermion bilinear with the monopole. So if you know this, then you can ask yourself, okay, what happens if I give a mass to the system? I'm using a time reversal invariant mass, okay? So a mass that gives opposite signs to psi1 and psi2. And if you do the RG flow, what you will get is that a mass will completely lift the base. right? Because you have to minimize this Lagrangian, and you will see that n has to be aligned with the mass direction. So once you give a mass, the S2 is lifted, you just get a point, and on this point there will be a circle. So this means that even for an infinitesimal mass, you get an S1 sigma model, which means you get a dual the photon, which is intuitive because you're saying I give a mass to QED, I can integrate out the fermions, I just left with Maxwell theory. But this happens even for infinitesimal mass. That's the consequence of our proposal. And other important points is that both the charge conjugation and time reversal are unbroken. You can actually prove that T is unbroken due to the Vafa-Witten theorem. And then, as I said at the beginning, there is a mixed anomaly between time reversal and U2, and this needs to be matched in the sigma model. This is possible because the sigma model, the third homotopy group of S3 is Z, and this means that the sigma model admits a conventional theta term that you can write in this way, where U is the pion matrix. And if you have time reversal symmetry, there are only two values of theta which are allowed, which are theta equal to 0 and theta equal to pi. And it so happens that theta equal to pi matches the UV anomaly. There is a technical computation to do to show that this is the case. In particular, you take this guy. These are dynamical fields. You couple to a background gauge field for the U2 global symmetry. And you can show that once you couple this to this background field, this term can be, the coupling can be rewritten exactly as a four-dimensional instanton number for U2 with some theta in front. So if theta is equal to pi, this is exactly the UV anomaly. Now, of course, we are not the first to study this problem. This problem has a very long history. The point is that in this long history, every time, well, most of the times that symmetry breaking scenario was discussed, it was only, people were only focusing on the breaking due to the fermion bilinear, which is the same thing that happens in four-dimensional QCD, where you have psi bar psi that condenses and breaks the chiral symmetry. But this will lead to just SU2 broken to U1. So you will only lead to two Nambu-Goldstone boson parametrizing S2. But what is easy to show is that this is incompatible with the anomaly matching. So you cannot match this anomaly if this is the scenario that is realized. You really need the third Goldstone boson, which is the dual photon. Okay. How did we, let me give you some checks of what we did. So first of all, what you can do is you start from the UV Lagrangian. You can couple the UV Lagrangian to some Cartan of the flavor symmetry and some magnetic, the U1 magnetic symmetry, the usual JA coupling. And then you can add a mass that is aligned along this Cartan. In this case, it's just the sigma Z, no? Plus m for psi1 and minus m for psi2. And then you can integrate out fermions at very large mass. This is an exact computation because it's perturbation theory. And what you get is that you will get the Maxwell term with some renormalized gauge coupling. And then this guy goes through. It is not affected by integrating out fermions because fermions do not carry charge under the magnetic symmetry, but they carry charge under the flavor symmetry. And this will induce a mixed Chern-Simons term between the original gauge field and this background gauge field for the U1 symmetry. And this term depends on the sign of the mass. So this is the low energy Lagrangian, and you see that this Lagrangian is telling you what is the charge of the monopole that is condensing, because the monopole is just a flux for this guy. So if M is positive, the monopole that is condensing has +1 charge under the magnetic and +1 charge under the flavor. If this is negative, then it has +1 under the magnetic and -1 under the flavor. And this is exactly the same pattern of breaking that I was describing before in the small mass regime. So the most economical scenario is that the large mass and the small mass regimes are continuously connected. And in this case, this exact computation is matched by our proposal at small mass. Of course, we cannot prove exactly that these regimes are continuously connected, but what we can prove is that at least for any mass, there is a photon in the theory. So this is a piece of evidence that is reasonable to think that the large and small mass regimes are connected. Okay, and another very powerful tool that we use to constrain the dynamics of this theory is the Vafa-Witten theorem. So the Vafa-Witten theorem imposes strong constraints on the allowed patterns of symmetry breaking in time reversal invariant theory, like QCD. And naively, one would say that vector-like global symmetry cannot be spontaneously broken. This is the usual terminology, but this is not true for QED. There is a subtlety. There can be a mixing between the vector-like global symmetry, which is the flavor Cartan of SU2, and the magnetic symmetry. So once you take this into account and you apply the Vafa-Witten argument to QED, you get that you can prove the following conclusion. So first of all, time reversal is unbroken. Second, that if no monopole operator condenses, then both the Cartan and the magnetic symmetry are unbroken. And third, if there is a monopole that condenses with some charges, magnetic and flavor, then there is a specific linear combination of the flavor and the magnetic symmetry that is unbroken. So first of all, this explains the alignment that I was telling you before. So the fermion bilinear has to be aligned, because if it was not aligned, it would further break the U1, and this is prohibited by this. And basically, our proposal realizes point 1 and point 3 with the minimal monopole, with the magnetic charge 1. Okay. How much time do I have? 5 minutes? Yeah. Okay. All right. Okay, now I want to take some time to describe some work in progress that we did. So this is the story for the non-supersymmetric theory, so quantum electrodynamics with two fermions. I told you at the beginning that we're assuming that the NF equal to 2 theory is not conformal. We are borrowing these results from the bootstrap. And now I'm trying to argue that the supersymmetric theory offers some insight of why this is the case. So what we do is to start from a version of supersymmetric quantum electrodynamics with 8 supercharges, so n equal 4 supersymmetry in 3 dimensions. And you take one hyper of charge 1. So the field content is a photon, a triplet of real scalars, the gauginos, then there is a doublet of complex scalars and a doublet of complex fermions. This is the hyper, and this is the vector. And I and I prime are SU2 indices. There is a left and a right are symmetry, and then there is also the magnetic symmetry. So the supersymmetric counting is different from the non-supersymmetric counting because one hyper means 2 fermions, okay? Now, this theory has been exactly solved in the 90s by Seiberg and Witten. They show that this theory has a Coulomb branch of vacua that is 4-dimensional and is parameterized by the dual photon sigma and the 3 real scalars in the vector multiplet. And the point is that this Coulomb branch is smooth and singularity-free. And you know everything about it. It's a sigma model with some target space metric of the Taub-Nut type of this form. Right? So it's written in terms of the coordinates, phi 1, phi 2, phi 3, and the dual photon. And there is, you see there is the vibration here. And V of R is some corrected gauge coupling. Now, by mirror symmetry, this Coulomb branch can be dualized to the theory of a free twisted hypermultiplet. Twisted just means that while the ordinary hypermultiplet, the boson is a doublet of the right symmetry and the fermion is a doublet of the left symmetry. Twisted is the opposite, so the boson is a doublet of the left symmetry and the fermion is a doublet of the right symmetry. But this boson is nothing but the monopole operators because you can compute the charge of this guy and this is just the monopole. So this means that the Coulomb branch can be equivalently described by, parameterized by the VEV of the monopole operators. So if you're anywhere on the Coulomb branch, the monopole is getting a VEV. If you're at the origin, the symmetry is unbroken. So the symmetry acting on the Coulomb branch is really only the U2, only left and magnetic. There is no trace of the R symmetry. And this is the same symmetry of QED3 that I was describing before. Okay, so this is the supersymmetric theory that has a flat direction. Now I want to break supersymmetry. So I break supersymmetry by deforming the theory to give mass to everything, the scalars, the photinos, and the complex scalars, but not to the gauge field and the fermions. But I don't do this randomly. I do this by using components of multiplets that can be reliably tracked in the AR. For instance, using the components of the stress tensor multiplets. And this is a procedure putting forward by Clay Cordova and Thomas Dumitrescu by thinking in 4-dimensional adjoint QCD. So you use protected multiplets, and using protected multiplets, you give mass to everything but these guys. So this means that you take the UV Lagrangian, you add the deformation, and the theory flows to the theory that we want. It flows to non-supersymmetric QED with 2 fermions. It's the only thing that remains massless. But now you can track this deformation to the IR. So you do this tracking because you're using a protected multiplet. And in the IR, it turns out that this deformation switches on a non-trivial scalar potential on the Coulomb branch. So the Coulomb branch is not flat direction anymore, but part of it is lifted. So you do the computation and you get that the minimum of the scalar potential is at some value of R, which is non-zero. What does it mean? It means, first of all, that the global symmetry is broken because only the origin of the Coulomb branch is where you have unbroken global symmetry. Then the target space metric is what? Is a foliation of this space at R equal to constant, but this is exactly an S3 sigma model with the vibration. And you recover the U2 broken to U1 exactly via the monopole condensation because the point on the Coulomb branch are parameterized by monopole VEV. So using this supersymmetric theory, we're able to give evidence that our proposed scenario is indeed correct. If the theory does not flow to a CFT, of course, which is something, yeah. Okay, so let me summarize. So what we propose is that the symmetry breaking in quantum electrodynamics is driven by monopole operators, and they carry both magnetic and flavor quantum numbers. So the symmetry breaking is not only driven by fermion bilinears, as it is instead the case in usual four-dimensional QCD. And then we used some arguments related to the Vafa-Witten theorem, Toft anomaly matching, and the perturbation theory for large mass. And we gave evidence that if the theory is not a CFT, then U2 is broken spontaneously to U1 via the condensation of the monopole. And this gives rise to an S3 sigma model with a theta equal to pi term, which matches the anomaly. And one of the Nambu-Goldstone boson is always the dual photon. This is valid for any NF if you generalize this story. And I show you how this is consistent with the RG flows from supersymmetric QED with one hyper. And one last observation is that if you perform the same trick with a supersymmetric version of QED, but with more hypermultiplets, now the Coulomb branch has a singularity at the origin. And the singularity at the origin means usually that there are additional massless degrees of freedom there. So it's compelling to think that in that case, what will happen is that you will be sucked in the origin, and the theory indeed for 2 or more hyper, which means 4, 6, 8 Dirac fermions, then it has a different behavior, which is a CFT-like behavior, and this will be very nice because the supersymmetry and the bootstrap will lead to the same result. Okay, thank you.
Question, Elias?
When NF is odd, there is a parity anomaly, but that's not bad for the theory.
No,
is
sure.
it known what happens there?
Yeah, okay. The point is that our treatment, we use heavily the Vafa-Witten theorem that can only be applied to time reversal invariant theory. And if NF is odd, you don't have this tool. But I think there, I think that this is a CFT for any value of NF, if I'm not mistaken. Yes, yes. It's really two different theories, NF even and NF odd. It's really, they have nothing to do. Yeah.
Okay. You mentioned previously people only consider the symmetry breaking induced by the fermion bilinears.
Yes.
And then they miss one Nambu-Goldstone boson.
Yes.
So what's the logic there? Like by omitting one possible other parameters, we. Like,
so here, yeah, the people were motivated in. Well, there was the idea that fermion bilinears were responsible for symmetry breaking.
Yeah.
And since time reversal has to be preserved, you cannot have a condensation of the singlet of psi bar psi. Okay. You have to have a condensation of the triplet, right? Psi bar, sigma, psi. But this will be like, it's like Georgi glass, no? You have a field in the joint, and the SU2 is broken to U1, and this is two Nambu-Goldstone boson.
Yeah, okay.
And this was motivated by the fact because this operator is time reversal invariant. People knew that the only thing that can condense is time reversal, has to be time reversal invariant. And then the most natural object is the fermion bilinear, because it is the same thing that happens in QCD.
By the way, can I also ask about terminology? Why is it called dual photon, the Nambu-Goldstone?
Well, because the third Nambu-Goldstone boson, okay, good. It's here, no? So the two Nambu-Goldstone boson that parameterize the base, yeah, they are in the triplet representation of SU2, and they're singlet under the U1.
Yeah.
Then, so I give you N. Once I give you N, what is M? Well, it's not enough that I tell you where I am on the base. I have to tell you where I am on the circle. But this circle is charged under magnetic symmetry.
Okay.
And the photon is exactly the Goldstone boson for this breaking, for this sigma model.
Yeah.
So the fiber is exactly the dual photon.
Okay, thank you.
Thanks. And there, in the paper by Shai and Zohar, they also had this other axis where they deformed with a mass term that was not sort of adjoint SU2 times U1 symmetric. Does your SUSY analysis say anything about that? Can you extend in that direction?
Yeah, that's a good question. So,
but that is interesting, like phase transition to gap phase
right.
and some 04 point.
Yeah, you see, the problem is, okay, for the SUSY, we're trying to do this. So this is work in progress. I can tell you the difficulty is that once you allow yourself to break time reversal, which is what they did because they are adding the singlet mass, it's very difficult to claim that the theory exactly flows to what you want, right? Because here I'm giving a time reversal invariant mass to these guys. And so I managed to preserve this. If I want to also explore this direction, I'm giving mass simultaneously to everything. So I need a hierarchy to say that first I integrate out these guys, and then I can say that I have QED with fermions. Okay. So I'm not protected by time reversal to distinguish psi between the other guys that are integrating out. So it's more difficult. We are working on it. Also because you cannot do it randomly. You have to use multiplets that can be tracked on the Coulomb branch. Otherwise, you're not doing anything.
Sure.
Yeah.
Thanks.
Well, if there are no further questions, let's thank our